We have two more formulas for this section, and that is the sum and difference formulas for tangent. And let's see what those look like. Tangent of alpha plus tangent of beta all over 1 minus tangent of alpha tangent of beta. And one neat thing about these ones is you can prove this identity here just using the fact that sine of alpha plus beta over cosine of alpha plus beta is equal to tangent of alpha plus beta. You would just need to apply those new sum formulas for sine and cosine. Now the other one here, tangent of alpha minus beta, this is going to be equal to tangent of alpha minus tangent of beta all over 1 plus tangent of alpha tangent of beta. All right, example 4, we are going to try and apply this identity. And by this identity, I mean the sum formula for tangent. Okay. We'll refer back up to this, but note, if I want to find tangent of alpha plus beta, we can at least remember that the numerator is tangent of alpha plus beta. And the reason I say that is if we, say, decided to start with this side, trying to verify this identity, well, we could start with the new identity, which is that we should end up with tangent of theta plus tangent of pi over 4. And then let's remind ourselves of what the denominator looks like when we have tangent of the sum of two angles. It should look like 1 minus tangent alpha tangent beta. So 1 minus tangent of our first angle theta tangent of our second angle pi over 4. And now it actually ends up that we can simplify this example in a different way than we've been able to do any of the previous ones. We know what tangent of pi over 4 is. It's 1. So we're going to replace our tangent of pi over 4 with just 1 here. And that's going to give us tangent of theta all over 1 minus tangent of theta. And right now, this isn't really looking like this up here, is it? But something good has happened. The argument, that's the name for the thing that's inside the trig function here. We went from theta plus pi over 4 to just theta. And that's helpful because the right-hand side of the equation doesn't have any theta plus pi over 4s. It only has thetas. So this is not all bad. The one thing that we're missing though is sines and cosines. Well, that's an easy fix. We know that tangent of theta is equal to sine of theta over cosine theta. And we might be running out of room here a little bit. Let's see. So sine of theta over cosine of theta all over, does anybody see what I am missing? I said that we were going to turn all those tangent of pi over 4s into 1s. So we should have a tangent of theta plus 1 here. Now, unfortunately, these two things are not going to cancel out in any way. Okay? If they were the exact opposite signs, then yeah, we could cancel something, but They are unfortunately not opposite sides of each other. Okay. But we can still continue this process, writing everything in terms of sine and cosine. And I'm actually going to do one more thing in this step. I want to get a common denominator. Okay. And specifically, the place I'm going to get a common denominator is I'm going to get one so that I can add the two things in the numerator, and I'll try and get one so that I can add the two things in the denominator. Okay. Or, better yet, there's another strategy we could take. If we don't want to get the common denominator, we can actually multiply the numerator and denominator by cosine of theta. Why is this helpful? Well, this is helpful because we will wipe out those cosine thetas that are in the denominators of some of these fractions. So cosine theta times sine theta over cosine theta is just sine theta. Cosine theta times 1 is cosine theta. And then this is all over. And then 1 times cosine theta is cosine of theta. And sine of theta over cosine theta times cosine theta is just minus sine of theta. And notice that this is exactly what the right-hand side is, with one exception. In the numerator, we have sine of theta plus cosine theta, while the original equation has cosine theta plus sine theta in the numerator. Remember, the order of addition doesn't matter. Addition is commutative when we're working with real numbers. Okay. So we are done. Let's look at one last example here for this section. And we're going to be thinking about cosine of alpha plus beta. But in order to figure out cosine of alpha plus beta, we are given some more information. We're given some information about cosine of alpha and some about sine of beta. Well, why is this helpful to know these things? Well, it's helpful because if we have cosine of alpha plus beta, we can maybe rewrite it in terms of cosine alpha and sine beta. Right? We know that this is equal to cosine of alpha, cosine of beta, minus sine of alpha, sine of beta. Next, we can draw maybe a couple pictures. Okay? Let's draw ourselves a picture of this cosine of alpha equals 1/2. So alpha is said to lie in quadrant 4. And let me actually use one of these arrows here. There we go. So I'm just going to sketch an angle in quadrant 4. Done. And we'll create a triangle out of this. We know that cosine of alpha is equal to 1/2. And remember, cosine is adjacent over hypotenuse. Okay. And if we use our Pythagorean theorem, we can figure out this missing side here, because maybe we'll want to find sine of alpha here in a minute. Okay, well, if we do that, we have 2 squared is equal to 1 squared plus x squared. So we have 4 is equal to 1 plus x squared. And so you can see we get 3 equals x squared. And so therefore this missing side must be equal to the square root of 3. And I'm going to get rid of our Pythagorean theorem work just so that this doesn't get too messy here. But let's also draw a picture for sine of beta. All right, here's our axes. We know that beta lies in quadrant 3. Let me try that again. Okay. So there's our initial side, and here is our terminal side. Except for I want that terminal side to be in quadrant 3, so I'm going to move it down here. And once again, we'll make a triangle out of this. And one more thing about these pictures, if we're being really technical, this is the reference angle for alpha. Okay, right? Alpha is actually the angle that would go all the way around here. Okay. And rather than this being beta, this would really be beta prime. That'd be the reference angle for beta. Okay. But sine of beta is equal to opposite over hypotenuse. So the opposite side should be 1. The hypotenuse should be 3. And again, using our Pythagorean theorem, we have 3 squared is equal to 1 squared plus x squared. And so we get 9 minus 1, which is 8. And if you solve for x, we get x equals the square root of 8, which can be written as 2 square root of 2. Now, once again, I'm going to get rid of our Pythagorean theorem work because we can now use this equation up here. And I'm going to move this equation down so that we can keep our work all close together. There we go. So we know that cosine of alpha is equal to 1/2. That was given in the question. Cosine of beta, though, we did not know. We're going to have to use this picture here of the angle beta, or beta prime. Okay. So cosine of beta should be adjacent over hypotenuse. So if we take the adjacent side over the hypotenuse, that's 2 square root of 2 over 3. We do have to be careful about one thing here, though. Cosine in this quadrant, specifically quadrant 3, is negative. And then sine of alpha, we weren't given that. We're going to have to use this picture here. Sine is opposite over hypotenuse, so we're going to have the square root of 3 over 2. And once again, I need to think about, is sine positive or negative in quadrant 4? And it is actually negative. And lastly, we have sine of beta, which we were given that sine of beta is minus 1/3. Let's start doing a little bit of simplification here. Note that we could start multiplying things. We have minus 2 root 2 over 6, and then we have a triple negative, so minus the square root of 3 over 6. And then we have the same denominator for both of these. So this gives us minus 2 square root of 2 minus the square root of 3 all over 6. And we're done.